So this is a review of what we did in class today. This is the mole concept. So if I have just one single atom of copper, it would have a mass of 63.55 AMU. If I have a mole of copper, however, it has a mass of 63.55 grams. Same number, but different units. So an atom is very, very small, so it has a very, very small amount of mass, just AMU. A mole of copper is kind of a more measurable quantity. That's something you could measure in a lab. 63.55 grams. And that is the same as saying that I have Avogadro's number, 6.02 times 10 to the 23rd atoms of copper. This works for things besides just individual atoms, though. It works for ionic and covalent compounds as well. So for example, if I have one formula unit of sodium chloride, that means that I just have one single sodium ion and one single chloride ion. Its total mass, the mass of the formula unit, you would add the individual masses together. 22.98 AMU for sodium. You're going to look at that up on the periodic table. 35.45 AMU for the chloride ion. Add them together, 58.43 AMU. That's for one formula unit of sodium chloride. But if now I have a mole of sodium chloride, now I would have a mole of sodium ions and a mole of chloride ions. Ratios. I would have Avogadro's number of sodium ions and Avogadro's number of chloride ions. A lot. The mass of one mole of sodium chloride would be the mole, add together the molar masses of the individual components. So 22.98 grams for my mole of sodium and 35.45 grams for my mole of chloride. Add them together, get 58.43. So it's the same number again, but different units. If I'm talking about a little teeny amount, one formula unit, it's going to be an AMU. For a mole, this is now a more measurable quantity, something you could do with a balance, 58.43 grams. Works for carbon dioxide as well, for covalent compounds. A molecule of carbon dioxide is one single atom of carbon and two atoms of oxygen. You would use this formula to find the atomic mass of a molecule of carbon dioxide. So 12.01 AMU and 2 times 16 to count for the two atoms of oxygen, 44.01 AMU. But if it's a mole of carbon dioxide, now I have a mole of carbons and 2 moles of oxygen. So I'm going to have to add together carbons' molar mass, 12.01 grams, and 2 times oxygens. Put that all in one line in your calculator, 44.01 grams. So again, molecules or atoms, it's AMU, but if you're talking about moles, now it's the same numbers, but grams. So we are, of course, going to use conversion factors for these. And this is the basic conversion factor so far, is that 1 mole of a substance is Avogadro's number, 6.02 times 10 to the 23rd particles of the substance. Now, particles could be atoms, they could be formula units, or they could be molecules. Just individual smallest pieces that you can get. So if it's copper, it's going to be atoms, NaCl formula units, carbon dioxide molecules. Here's a typical problem. How many moles of CO2 are 1.48 times 10 to the 24th molecules of CO2? So you're going to set up your conversion factor. Start with the given information, number, unit, and substance. You want to get rid of molecules of CO2, so they go on the bottom. You want to end up with moles of CO2, so they go up in the top. Then put your numbers in. 1 mole of CO2 is the same thing as saying I have Avogadro's number of molecules of CO2. Again, molecules of CO2 because this is a covalent compound. Molecules is the word that applies for covalent compounds. So then you need to put it in your calculator. Again, you multiply everything across the top, which is just going to be your number times 1, and divide by everything in the bottom. Make sure that you are using that EE button when you're using numbers in scientific notation. 1.48 E24 divided by 6.02 E23. Again, it's that second button to give you that capital E. And you're going to get 2.46 moles of CO2, which is the whole reason we use this, because it's a whole lot easier to say that I have 2.46 moles of carbon dioxide rather than saying I have 1.48 times 10 to the 24th molecules of them. They're just huge numbers. In any kind of quantities that we would ever be able to work with or measure, it's such a huge number that we just want another way to describe it. In the same way that instead of saying how many eggs, you might say how many dozen eggs. For 1 dozen, it's no big deal, but if you have a lot of eggs, it'd be a lot easier to say you have 6 dozen instead of however many that would be, and I don't know what that is off the top of my head.